So for this geometry final review, you may have already seen part one. So if you already know what to do, then go ahead and skip to whatever questions that you want to review. If you haven't and you just happen to come across this one, take the exam. The link is in the description. And then once you've taken that exam, go ahead and check your answers. And whatever ones that you've gotten wrong, you go ahead and look at the description. I put timestamps next to each question, whether it's in this part or any of the other two parts. Make sure you go over the missed ones. I go in depth on the actual question itself. And then next to each of those questions in the description, I'll put a link to some extra practice problems so that you can get a little bit more practice in case you want to make sure that you're comfortable with whatever the topic might be. So that's pretty much how these ones go. So let's go ahead and get started. So for number 9, we've got a quadrilateral below, and they tell us that these two line segments are parallel. So as you know, I'm always going to go ahead and I recommend you always do mark those if they give you a diagram. And they tell us these are really important right here. E, H, and F are the midpoints of AD, AC, and BC. So I'm going to mark these. So AE, we know these two are parallel because E is the midpoint of that. H is the midpoint of AC, so we know that these are congruent. And if I said parallel for these, I meant congruent. But and then we know that F is the midpoint of BC, so we know that these two line segments are congruent. Now, this is going to use a theorem that you've learned, but you probably don't remember because it's one of those weird ones that you don't see a whole lot of unless you're actually on that chapter. But basically, this right here is a trapezoid. We've got a quadrilateral with parallel bases. That's a trapezoid. There's, I think it's called like the midline of a trapezoid theorem. I don't know if there's a proper name. It's something like that. If you Google midline of a trapezoid, you'll find this particular theorem. But what we're basically, I didn't even say what we're looking for. I marked out the lengths that they give us here. And we're looking for the length of line segment FH. I'll call that X. Let's do a different color. We'll call that X. So if you look, when I first see this, I'm looking at this triangle, this smaller triangle, CHF, and then the bigger one, CAB. If we can prove that those two triangles are similar, then we have something to work with pretty easily. Now, it comes with, the only way that that works is if you notice, these two triangles, the small one and the larger one, they share this angle in common, okay? So not only do they share that, but we can also prove using that midline of a, and there's probably another way to do this, I believe, but I want you to know this theorem as well. If there's a line that cuts through a trapezoid and it cuts both sides into congruent parts, so it's a mid, each point is a mid segment, just like this line, EF, is also parallel to the bases. So we know that all three of these lines are parallel. So now we can use our alternate interior angles theorem and all the other fun stuff. But in particular, I want you to think of one that we could use here. And if you look, all we need to prove that two lines are similar is that two angles are congruent. We already have one. This angle is included in both of the triangles. And if you look here, we can actually take our pick. Because these are parallel, if you look at angle B and angle, however you want to call this one, CFH, those are congruent by the corresponding angles theorem. And the same thing applies to this angle and this angle by the same thing, corresponding angles theorem. So we didn't even need to do both of those, but now we know that CHF and CAB are similar. Okay, that's the important part that I want you to remember. And if that's the case, what I want you to see with this one is that if this is 10, HC is also 10. So if you notice, the small side is half of the larger side of the triangle. So the small triangle length is half the size of the larger triangle length, the corresponding side. Now, if you look, HF is kind of like, think of it as the quote unquote, the bottom of the triangle, of the smaller triangle. AB is the bottom of the larger triangle. So those are corresponding sides. I don't know where I got rid of the X, but so X, if you think about it, should be the same proportion as these two. 10 is half of the whole thing, which is 20. This should be half of the whole thing, the larger triangle corresponding side, which is 24. Half of 24 is just 12. Okay, so I'm going to type this out again because that's something, if you can remember that formula, one, you'll have to. There's some questions you can't do. I can't even type. Midline I think it's midline of a trapezoid. And then it might not even be a theorem after it, but I'll just put theorem. So if you Google that, you'll pretty much see the same thing with all these markings here. But if you have the main takeaway from this, if you have a line that cuts through a trapezoid and it cuts each side in congruent parts, it bisects both of the sides, then that line is parallel to both of the bases, and that's going to be one, you have to know that to be able to solve a lot of the problems that come about from that, because then we can use all the fun parallel, corresponding angles, alternate interior angles, and things like that. And in this case, I think we could have gone a different route with it, but I wanted to show you this one because it will randomly pop up. And if you don't know it, like imagine seeing this and be like, I don't even know what that is. But if you do know it, which you do need to remember that, then you can say, oh, okay, well, that means that this is parallel. Now we can use some of those parallel theorems that you've learned. You did a whole chapter on them, and those are going to be super important. They pop up randomly on the final in various forms, so you have to memorize those theorems. But sometimes we have to take an extra step just to get to them, and one of them is this particular theorem here. So that's all we had to do here. It seems a lot more difficult than it is, and I ran over a little bit on this problem. I apologize, but I wanted to explain this because you will see this, I guarantee, in some form or another on the final. All right, now we get a nice conceptual problem. Always fun, but basically, they tell us some characteristics of two cones, and we're trying to find the volume of cone A. Now, first things first, we need to know the volume of a cone formula. They might give this to you on the final. It really depends on the teacher. Usually they do, especially if it's a standardized test. They might give you like a whole page of all the different formulas and whatnot. But this is one that you should remember. It's not as bad as some of the other ones. But basically, let's go ahead and write out what they give us. All right, so we're going to write out the volume of cone A first. So the radius of the base of cone A, this right here, pi r squared, if you think of the cone, that's the area of the base, pi r squared. So they're saying the radius of that base is twice as large as the radius of cone B. Okay, so I'm going to write this as pi times, I'm going to put r sub b to represent the radius of cone B. Now they say it's twice that, so I'm going to put 2. And for this formula, that's squared. So that whole thing, quantity squared, times the height, all divided by 3. Okay. The height we don't know. I'm just going to leave it as h. Now let's do the same exact thing, but for B. The volume of cone B, they say, the height is twice the height of cone A. All right. So we'll do pi. Now this is just, normal, the radius of cone B, quantity squared. Now the height is twice of cone A. So we could put like h sub A, the height of A. We'll put here, now it's 2 times that. 2 times h of A over 3. Now let's go ahead and simplify these. So if you notice up here, everybody probably, I guarantee a lot of people are going to forget to put this 2 inside of the squared. Remember, the whole thing is going to be squared because this is the radius of cone A. So if we simplify this a little bit, we'll get pi times 4 times r of b squared times the height of A divided by 3. And then for cone B, we get 2. So 2 pi r squared h of A. That should be an A right there. So let's write that again. I think I got carried away with my 2's. Let's try that one more time. A, there we go. And then all divided by 3. So if you look, I'm going to put this 4 out front just so it looks like the other one. If we strip away everything else, and I should have put a sub b down here. If we strip away everything else, notice what they have in common. This, rb squared, h of a, those are all up top. We can get rid of those. They're all divided by 3. We can get rid of those. And if you look, a is just b, but take a guess. Times what? Times 2. So the volume of cone A is just twice the volume of cone B. So that's, and it's confusing. A lot of people are going to be like, well, they're equal because I doubled the radius and I doubled the height. They cancel out, but the radius is actually being squared. So when you square that, the double, quote unquote, turns into a 4. All right, that's why we get the 4 versus the 2 over there. So that's Very important. A lot of people are going to pick 3, but that's why I always recommend just write it out. And I may have written it as like, oh yeah, super easy to write the formula, but make sure you know what you're writing it in terms of. Like, oh, okay, well, this is twice the radius of B. Okay, we'll put R sub B so you know what that is. That's the radius of B, and the radius for A is twice that. All right, and same thing over here. The height of cone B is twice the height of A, so just write it as H sub A so you know it's the height of A. You don't have to write those. It just makes it a little bit easier to read so you know what in the world's going on when we have, 6 different variables at times. But that's all we do. And the reason why I was able to strip away a lot of this stuff is you can take away what's in common and then figure out, okay, what's the difference? What am I multiplying by to get from cone B to cone A? And it's just times 2. And that's all we have to do for that one. So make sure you're comfortable with writing out the formula, obviously, but also being comfortable substituting in these values when they give you these word problems like this. Knowing how to write that. Twice the height, twice as large, put it in the radius. Make sure the 2 is also being squared and not just a 2 out here not being squared. That'll get you the wrong answer. That'll actually get you 3. So that's all we're looking for this one. It's kind of like a literal equation where we just have letters and there's really no numbers, kind of. There's not like a solution, but also being comfortable with you manipulating that formula like that. So hopefully that helped a little bit with this one. This is a little bit more of a difficult one, but it's really just plugging in the particular variables for each one. All right, we got some polygon stuff going on. I remember I never really liked these types of problems where it's rotated and, how do you get it onto itself after you rotate it? But it's really pretty straightforward when you're comfortable with this particular idea. And this is something that you have to memorize. A convex polygon, basically a convex polygon is just a polygon where every single interior angle is less than 180. Okay, so if I drew a polygon that was like, it looked like this, but then it was kind of like that. If you look, this angle inside is greater than 180, so that's not convex, that's concave. This thing I'm about to tell you, you probably learned it already, I hope, but this applies only to concave polygons. Regular just means every angle is the same, every side is the same length, okay? Every exterior angle, so if I continue the line for each of these, if I add up, and remember a hexagon has 6 sides, if I add up all of these exterior angles here, and they're all equal to each other, they're always going to equal 360 degrees. That's one thing you have to memorize, okay? If I add up any of those of a convex polygon, and in particular regular polygon, if I add up all the exterior angles, it's going to add to 360 degrees. The reason why I say that is because that's the number. If you take that 360 degrees, and you and I know that there's 6 sides, well, if I split that evenly between 6, we get 60, right? So each of these is 60 degrees. That's the number that you have to rotate by to get the polygon onto itself. When it means onto itself, that means you rotated it and it doesn't even look like you rotated it. It looks exactly the same. It'll look exactly like this. If I rotate this 60 degrees clockwise, this A will be right here. The B will be down here, and then so on and so forth. Everything gets moved down 1. Every letter F will come up here, all right? Now you might think, okay, well, 60 is not an answer. But I want you to take a guess. If you look at these answer choices, what would make the most sense from there? And if you said any multiple of 60, absolutely. If you take a look, 45, no, that's not a multiple of 60. 90 is not, 135 is not, but 120, that's just 2 sets of 60. So that's like, if I rotated this 120 degrees, the A would go 1, 2. The A would be down here. E would go 1, 2. E would be up here. But it would look exactly the same as this. You wouldn't even notice that it would change because now it's onto itself. That's what that means. So when you want to find how many degree measures you need to rotate something about its center to have that whatever polygon be onto itself, take the sum of the exterior angles, which is always 360, divided by the number of sides, in this case 6, that's the number that you need to rotate it by, whether it's clockwise or counterclockwise, to get it onto itself, or any multiple of that, 60, 120, 180, 240, so on and so forth, right? That's all you need to know about rotating a polygon, a regular polygon, such that it turns out to be onto itself. It literally just means it looks exactly the same in space. Okay, the points are going to be different unless you literally rotated it 360 degrees, then A would still be up here. But that's all that is. When it means onto itself, it looks exactly the same. It's not like, oblong like that. You can see why I didn't draw the polygon, but it looks exactly the same in space. Okay, so that's what that means. That's all you need to do for those types of problems. All right, so we've got a triangle and they give us some information about that. And we have here that MT is a perpendicular bisector, something that we definitely need to know what that means. Perpendicular meaning MT is cutting this line segment into it's creating two right angles, and then bisector meaning it's cutting AH into two congruent line segments. Okay, now if you look here, hopefully you remember back to the one chapter where you did all the fun triangle congruence theorems, side side side, side side angle. No, that was not one. Angle side, sorry. The hypotenuse leg, that special one. If you look here, take a second and see if you can figure out if there's a theorem that we could use to prove these two triangles congruent. I want you to remember, if you took a look at it, MT is part of both of these triangles, right? So we could put this right here, and then if you look, side, angle, side. So we just proved that MAT and MHT, or however you want to name those, there's multiple ways, both of those triangles are congruent to each other. Okay, so if we look here at number one, they're saying, okay, well, MAH is isosceles. That means that, and remember, they're saying which statement is not always true. So let's see first, is this always true? You and I know that this has to be, both of these triangles have to be congruent. And by, if you remember CP, this was fun, CPCTC, what was it? Corresponding parts of congruent triangles are congruent. Okay, so we prove that these two triangles are congruent. AM and HM are corresponding, so they have to be congruent. And if you remember, isosceles just means these two sides are congruent, and that has to always be true because we prove that these two triangles are always congruent based on what they gave us. So it can't be one because that's always true. So that's not always true. If we take a look at MAT, MAT is isosceles. What that would mean is that it's not always true. Well, all we have to do to prove this statement is figure out one instance where that's not true, and then we've already made this not always true. We just need to find one. I can't think of the word. A counter. Not a contradiction, but a counter example. I think something like that. I can't remember the word, but basically, I want you to imagine that we drew the same exact triangle. But let me draw it a little bit differently so it's a lot more obvious of what we're looking at. I'm going to draw something like this. Maybe like that. Not as flat as I wanted it to be. But if you look, this is a perpendicular bisector just like this one. Let's say this was, because we can make this, actually, let me make this really obvious. Let's make it actually extremely obvious, and then you'll see it. I'm going to draw it like that. Here's our perpendicular bisector. Now, if you look, this is perfectly fine. These two triangles are still congruent because this line right here is part of both of them. But this is definitely not isosceles. If you look, this is bigger than this. This is our hypotenuse. That's always bigger than either of the two legs. Okay, well, boom, right there. That's done. There's a counterexample. That's MAT over here, the left side, is not isosceles. These two sides are not the same. To be isosceles, they'd have to be congruent. So 2 is not always true. Actually, there's a lot of instances where it would not always be true. And then I leave it up to you to take a look at 3 and 4 at why those would always be true. And I'll give you a hint for, let's take a look at AMH. You can take a look at this bisector right here. And then for number 4, A, and let me get rid of all this stuff. A and, let me erase all that. A and TMH are complementary. Actually, I'm going to leave these in here. You're going to need, I'll give you a hint. You'll need these right angles to prove that this, I'll call it angle 1, and angle 2 are complementary. Remember, complementary means they add up to 90. Their sum is equal to 90. So that's always true. I leave that to you. But our one here is that MAT is not always isosceles. Okay. Okay, and we can draw that. We can draw this in multiple ways. You can make this line right here like huge, and then you would see like, okay, well that's definitely not isosceles, but it still satisfies what they gave us. Okay, so that's the main one here. It really just started with, okay, well, let's see if we can prove these triangles are congruent. Pretty much anytime you ever see something like this, if you can prove those two triangles are congruent, that's usually the right way to go. Sometimes it doesn't work like that, but that's, 80% of the time going to be the case. If you can, sometimes you can't. But you want to see if you can prove them congruent, because then we can do a whole bunch of stuff with that. So this is just how comfortable are you with proving triangles congruent, and then this right here, corresponding parts of congruent triangles are congruent. Okay, that's a big one. You need to know what that means. All right, so I think we actually have our first circle problem. So remember, it's a whole chapter on circles that I'm sure you're definitely familiar with because it's one of the last ones you cover. But in this one, it looks like we're given a couple of things here, and we're looking to find the area of a sector. Remember, if you hear the word sector, I want you to think of it's kind of like a piece of the pie. So we're looking for sector EBR. So we're looking for the area of this. And that's just kind of if you think of the whole circle as a pie, that's just a piece of the pie. We just need to figure out, okay, well, what fraction of the pie, quote unquote, do we want? So let's try and find that out. Hopefully you tried this already. And if you look, we know that angle TRE is 15 degrees. So this right here is 15. And we know that BE is 9. Now it's important to note that BE being 9, BE should look familiar to you. This is actually the radius of the circle. We're going to need to know that. The radius is 9. And for this one, if you remember, there's one, I don't know if there's a theorem for that, but an inscribed angle of a circle. So inscribed versus central. An inscribed angle is just an angle whose vertex is actually on the circle, on the outside of the circle, the perimeter of the circle, whatever you want to call it. A central angle has its vertex at the center. So like TBE, that's a central angle. To find, to go from here, it would help if you and I knew, okay, well, what is this angle right here? What is this angle covering the actual sector that we're going to be finding? Because then we can move from there, and I'll show you that formula that we'll use. Now from there, we can't really do anything just with that, but if we know that this is 15 degrees here, if you remember the intersected arc of an inscribed angle, I know that's a mouthful, the intercepted arc of an inscribed angle, in this case for TRE, it's this right here, it's this TE right there. That measure is double whatever the angle measure is if it's an inscribed angle. If it was a central angle, they would be equal. So let's say this was 40 degrees, then TE would be 40 degrees. But for inscribed, the angle measure is half of the arc measure. So that means, well, if this is 15, we know this arc right here is 30 degrees. And you might think, okay, great, now what? So if we know that's 30 degrees, if you look here, if we have a line going through the center of a circle, that line is a diameter. And if you remember, a diameter cuts the circle in half, so we should know, let me see if I can get rid of some of this, all this writing. We should know that TER, that's half the circle. If you remember, half of the circle is half of 360 degrees. That whole thing is 180 degrees, and we know that this is 30, so what are we left with for RBE? And if you did your math, you should subtract it from 180, subtract the 30, and we should get that that's 150 degrees. So I'm going to erase all this stuff so it looks a little bit prettier. We just found out that angle RBE, the central angle, is 180 degrees. Whoops, that's a 0. Sometimes it turns into a rectangle. 180 degrees. Nope, not 180. 150 degrees. Sorry. 150 degrees. And what's really important is if you know the central angle of the sector that you're trying to find, that tells us, or we can use that value to find the fraction, because we know the entire circle is 360 degrees. You and I only care about 150 degrees of that circle. So that's going to be our fraction. Figure out what that number is. I think it's like 0.44 something. And then we take that, and instead of just taking the entire, area of the circle, which we know is pi r squared, we do that, but then we multiply by whatever the fraction is that we're looking for, okay? And that's how you find the area of a sector. You're really just doing the area of the circle times whatever the fraction is that we're looking for. So if we were looking for half the circle, Well, half of a circle is 180 degrees. We would put a 180, and 180 over 360 would give us half. So that makes sense in that regard. So if you ever forget, use an easier value. If you forget this, fractional part right here, think of 180, and you'd be like, oh, that's half. Oh, okay. So if I can find the central angle of the sector that we're looking for, that'll give me that's what I can use to find the fraction of what we're looking for. Now we know the radius, luckily already, that is 9. So we plug this in. And if you do, and 9 squared is 81. If you do 81 times whatever this is, again, it's like 0.44 something, you're going to get 33.75. And notice they leave the pi on there. So we just want this in terms of pi. And that's all we do for this one. So we used, in this particular case, I'm going to type this out because you need to know this. We use inscribed angles. You need to remember that relationship to its, I think it's intercepted. I don't think it's intersected. I think it's intercepted arc. And that's really where just, if you draw the angle out, it's just where does it cover the circumference of the circle? What's kind of covered by this particular angle? And in this case, for inscribed angles, it's half of the arc. If it's a central angle, it's equal to the arc length, the angle measure. Okay, so 2 things you have to memorize. And then this one right here, so much fun. But that's all we do for this one. The actual measure, the actual formula, if you want to know it, just to put it in general terms, is theta times pi r squared. Where theta can be, in this case, it's in degrees. Theta is the degree measure of the sector, the central angle of the sector that we're looking for. So that's why I started out with that. We need to find that. And to do that, we had to get this 30 degrees. We know this whole half of the circle is 180. Subtract it, and we get 150. And that's what we plug in. But this is the general formula, okay, over here for finding the area of a sector, okay? Now, if it was in radians, obviously 360 degrees, that's 2 pi. We would just need this to be in radians as well, okay? And that's all we do for that one. All right, so we've got Lou here who's got a rectangular prism that we have specific dimensions for. And we're trying to find out, based on a particular cost per cubic inch, how much does this brick weigh? So what we're doing here is, if you can imagine, if you see something to the third power, that's a dead giveaway that we're looking at volume when we're talking about geometry. Okay, so you can imagine, okay, well, and when you think of volume, in this particular case for a rectangular prism, that's one of the nicest ones formula-wise that we come across. Length times width times height. Y'all have probably known that for a while. So it would probably, be the best thing for us to do is, okay, well, first thing, we need to figure out what is the volume, because if we're given cubic inches, we need to know the volume. So we take that, 8 times 3.5 times 2.25. Obviously, this would be a calculator question. But once we do that, we get, I believe, 63. So we have 63 cubic inches. That's what the brick volume is. And we know that for every cubic inch, it's 1.055 ounces. How much does this weigh to the nearest ounce? So if you remember your fun dimensional analysis from back in the day, we can just write it like this. I do want you to see this. You don't have to write it like this, but I want you to know how it looks in terms of dimensional analysis. Dimensional analysis just means we write essentially fractions where the units cancel. So 63 inches cubed times, and if you remember dimensional analysis, we want these units to cancel out. So inches cubed is going to go on the bottom, or cubic inches, and we know that for every 1 cubic inch, it's 1.055 ounces. Now, if you notice, inches cubed, there's 1 in the numerator. I could put a 1 over here. There's 1 in the numerator, 1 in the denominator, and we're just multiplying these two numbers together. And our final answer, the only units that we have left are ounces, which is exactly what we want. So if you multiply this out, 63 times 1.055, you get roughly 66. It's like 66.4 something, but that's all we want. We just want the nearest ounce. So all we're doing for this one is figuring out what the volume is, and that's coming from this. I want you to immediately think, oh, cubic inches, cubic whatever, volume. We need volume. Okay, and then once you do that, if we just multiply these out. And if it's helpful for you that you write out, the dimensional analysis so that the units can, it's a really great way to make sure you get the right units in the answer. Because if you end up and you do this and you still have like inches somewhere, then something went wrong. So that's a nice way to check your answer. You don't have to write it, but it's a good way to just to make sure you get the right units in your end result. Okay, but that's all we're doing for this one. Find the volume, multiply it by what we have here. Okay, just as a disclaimer before we start this one, quadrilateral properties is one of the biggest topics in geometry, and you definitely want to make sure that you're comfortable with all of those. So with the parallelograms, the different type of parallelograms, their properties and things, I know it can get overwhelming with all the different types, but something that you definitely have to remember, especially in this case where we have a rhombus, and essentially it's being rotated about some point, and we want to find the measure of CAD. So KNM. We want to find the measure of KNM, this whole angle right here. That's what we're looking for. So if you can imagine, if they rotated this, and it's mapped, when I mean mapped onto this rhombus, that means these rhombuses, whatever that is, are the same when we rotate this, okay? So what I want you to see is, this is 35 degrees. Now there's a couple ways you could think of this, but I want you to imagine angle ADC and what the corresponding angle would be over here, because they're going to be congruent. So if we can find that, then we're going to look pretty good. So let's try that. And the best way that I like to do this when you're given the letters, I teach this to everybody, is if you look at ADC, that goes first, fourth, third. That's going to be the same over here. First, fourth, third. So KNM is the corresponding angle to ADC. Now if you look right up here, that's where the 35 is going to go. So right in here. Okay. Now, if you weren't comfortable with that, there's a couple other ways that we can describe it, but I do want you to be comfortable with that idea that corresponding angles or sides can be determined based on the ordering of the letters in the actual, definition right here. So AD, side AD, that's first and fourth, is going to be congruent to side KN, first and fourth, KN right here. That's why we know the 35 goes in here, okay? Or you can think of it as, well, this is angle CAD, so CAD, third, first, fourth, third, first, fourth, MKN, MKN. That's where this 35 is, okay? So that's a really nice way to kind of figure out what are the corresponding angles just by looking at the ordering of the letters in the definition that they give you, A, B, C, D, K, L, M, N, just instead of having to guess, because I remember I tried to do that by looking. I had very bad spatial awareness in geometry, so it really helped me out. So I hope it's something that you can use. But now that we know this, here's where we really get down to the rhombus properties. Rhombi, whatever, they are, the angles are cut in two, okay? So this is bisected. These two angles are congruent. If you and I know that this is 35, that means this has to be what? That also has to be 35. And it's like, okay, great. So we know that this whole thing right here, I'm going to get rid of this. We know this whole angle is now 70 degrees. That's property one. There's multiple properties for rhombuses, but that's property one. The angles, the interior angles are bisected by these diagonals. By the diagonals, excuse me, that's what I should have said. And then here's the second important property. Consecutive angles, meaning angles that are right next to each other, they are supplementary. Okay, supplementary, you should remember, means they add up to 180. Okay, and that's what you and I are looking for. We're looking for KNM. We're looking for this whole thing right here. Well, if we know that 70, we'll call this X, angle X. You probably already done the math already, but if we know that those two angles, KNM and NKL, these two angles are supplementary, well, they add up to 180. Do a little bit of math, and we say, all right, well, this is equal to 110. Subtract the 70 from both sides, we get 110. That's all we do with that. So for rhombuses, and correct me if I'm wrong in the comments if it's rhombi, I'm not sure, I can't remember. But multiple rhombuses, the rhombus property is that diagonals bisect the interior angles, and consecutive angles are supplementary. Okay, that's two of the big properties. There's obviously more for this particular type. That's why you have to know your quadrilateral properties. Okay, super important. There's multiple questions that you will get stuck on if you don't remember them, but with practice, it'll be like the back of your hand, I promise. So that's all we have to know for these two, those two particular properties. All right, so number 16 is always a fun one, and it's really where, if I'm not mistaken, this is where we're going to be using the geometric mean. If you don't know what that is, then I'll show you probably in this problem. So basically, here's the important points of this one. This entire triangle, RST, is a right triangle, and we have an altitude SV that's drawn to the hypotenuse of the big triangle. Hypotenuse, no, not hypotenuse. Altitude, remember, just means it's a line drawn from a vertex to the other side of the triangle, and it creates perpendicular. It's a perpendicular bisector on the other side. So these right here are right angles down here. Let me try that a little bit better. So that's super important to know, because what happens when and you've probably seen these problems before, is that creates three similar triangles when we have a right triangle with an altitude drawn to it. Now I can actually demonstrate that to you real quick. If you don't want to hear the demonstration of why, skip ahead a little bit. But let's just pick random values. We know that RST is a right triangle. So R or S, angle S, is the right angle. So let's pick two random, values that add up to 90. Let's pick nice ones. This one's 30 and this one is 90. Now you and I know that these two smaller triangles are also right triangles because of the altitude that was drawn. So this is 90, this is 30. This has to be, you can do some math, that has to be 60. All triangles add up to 180. All the interior angles add up to 180. I don't know why I put 60 here. I can't do math today. That would be 60. Excuse me. 60 plus 30 is 90. Well, in this triangle, VST, whatever you want to call it, if that's 90, that's 60, this has to be 30. So if you look, the angles of the smaller and the bigger triangle and the biggest triangle, they're all the same. So if you remember your angle similarity theorem, if two corresponding angles of two triangles are congruent, then the two triangles are similar. That's super important to know. All right, so now we proved all three of the triangles are similar. Now, this is what I like to do, just to make it a little bit easier so you're not having to guess what side corresponds to what. It takes a little bit more work up front, but I promise it makes it a little bit more organized. I like to draw the triangles. So let's draw the triangles. So we're going to say, all right, this one right here, here's the small one. That's RVS. That's V. This looks like R. That's R. And this would be S. The bigger triangle looks like that would be, so the right angle is V. Looks like the top would be T. That's a T. And then this would be S. And I'm going to have to move over a little bit to do the biggest triangle. That's a triangle. And then we have that one right there. We already know S is the right angle. The side right here is R. And the top is T. Now let's draw what we know. We know that VT is 10.2. We know that RV is 4.1. It's going to get kind of small here. 4.1. And we know that ST is X. So anywhere you see an ST, we'll put an X. X, I think I erased something accidentally. Where's the S here? There we go. ST is X. And then there's one more that we don't know, but we can find it. If you look, if I add up these two together, I get the hypotenuse of the big triangle. So 10.2 plus 4.1 is what? 14.3. So the hypotenuse of the biggest triangle is 14.3. Here's the tricky part. We can't do anything else. If you remember from here without the geometric mean, what I was mentioning before, because what you know here with all these right triangles is normally you do the Pythagorean theorem, something like that. But here, this is what you need to do. The geometric mean basically means this. I'll give it to you in the formula form, but let's say we have a value y, and we want to find the geometric mean of it. Or basically how they'll ask the question is, what's the geometric mean between 3 and 9? I just picked those numbers randomly. What you'll do is you'll do this, 3 over whatever the mean is, equals the mean over 9. Let's try that again. That's an M. So what you would do is you would cross multiply, and you'd end up with m squared equals 27, and you would take the square root, and that's what you would get. Root 27 would be the geometric mean. That's how you find the geometric mean between blank and blank. You've probably seen that question before. What's the geometric mean between 10 and 2? Do the same exact thing. Replace this with whatever you want, 2 or 10. It doesn't matter what order those go in. But the geometric mean, the variable that represents the geometric mean, it has to be the denominator for one fraction and the numerator for the other fraction. When we cross multiply, we need to get a squared value. Okay. Now, here's the fun part. And that's why I draw this out, because it makes it so much easier. Basically, what you're looking for is what fraction can I create? Because we know all these triangles are similar. You can imagine there's no x here, so we're not going to be able to use that one. But between these two triangles, what do I need to set up? What fraction do I need to set up so that the x's are on opposites? So one, it's a fraction in one, or sorry, it's a denominator in one fraction. It's a numerator in the other fraction. So if you look, we have, I just call them by their where they are. Left side, we can draw, and again, there's a couple ways we can do this. Left side divided by the left side. And again, we can do this because their corresponding sides are proportional because they're similar triangles. That's why you have to know what similar means. Equals the hypotenuse over the hypotenuse. Hey, look at that. It's on the bottom on one fraction, it's on the top on the other. I could have done it the other way. X over 10.2 equals 14.3 over x, and they still would have been on opposite sides. Okay, just the numbers would have been flipped. So now we go ahead and cross multiply. I don't know what that is because I haven't done it yet. So let's figure out what that is. 14.3 times 10.2, we get 145. Well, if I cross multiply the other one, I get x squared equals 145.86. And if I take the square root of that, which definitely just did right now, we get roughly, if I root both sides, I get x equals, now we would get a plus or a minus. We don't care about the negative here because we're talking about length. We only want the positive version. So it's roughly 12.077. If we round it to the nearest tenth, we get 12.1. So I'll put a little approximate, it's approximately 12.1. That's what you do with these types of problems. When they give you a right triangle and there's an altitude drawn, automatically I want you to think, wait a minute, okay, I just have now three, the small, the medium, and the big triangle. All of them are similar triangles. Now I can make proportions between corresponding sides. That's why I said, okay, left divided by left equals, hypotenuse divided by hypotenuse. It's however you want to write it as long as the proportion is correct. All right. And your goal, if you notice, you're not going to be able to do the Pythagorean theorem. As much as it stinks, that's why I hated these problems growing up. But what you want to try and figure out, that's why I write them out, because it's much easier to see, this side goes with that side, that side goes with this side, and it makes it much easier to draw your proportion, and that's where this geometric mean comes in. We basically just found the geometric mean between this number and that number. But we're using that here for these types of problems. So if you ever see a problem like this where you have, a right triangle, pretend that's a right triangle, and then an altitude drawn, like 99% of the time you're going to be setting up a geometric mean. Okay. And this went way longer than I thought, but I wanted to explain what in the world goes on here, because these do pop up on the SAT and the ACT, not just in geometry, and they're really weird if you don't understand what in the world is going on. Okay. So that's all we have to do for this one.